2-4, rates of change in tangent lines. This is where we're trying to get to. We talked about this very briefly earlier in the year, and we're actually going to repeat this lesson almost in its entirety in 3-1. Because from here, we're taking it as, let's talk about limits and how limits impact rates of change in tangent lines. And then suddenly in 3-1, we say, let's talk about the derivative and how we use limits of rates of change in tangent lines to create it. So we don't use the word derivative here, but that's what it is. We are creating a derivative, right? So this is average rate of change. What you will see in a lot of people's work as AROC, average rate of change, always catches me off guard because I never use the abbreviation. And this was on the AP problem that I had a grade last year, so you should definitely know how to do it. It just basically means the change in Y, which in this case is that on top over the change in X on bottom. Now this is a little dicey. You got to put in 3 to the third minus 3 minus 1 to the third minus 1. And something's bothering me about that. 3 to the third minus 3 minus 1 to the third minus 1. Hopefully that's correct. I feel like I've done something wrong. Let's see if I can figure it out. Yeah, that was stupid. Insanely stupid. So it's just X. 3 minus 1. Must be too early in the morning for me. But anyway, this is the 3 to the third minus 3. I can't believe I just did that. 3 to the third, 27 minus 3, 24 minus 0, 1 minus 1 over 2 equals 12. Now, this is where I'll put my units in and I'll read the question carefully. Average rate of change over the interval. There are no units. There are no units given here. Let's assume it was meters per second, well, then we would write in meters per second. Well, let's assume it was feet per second, then we'd write in feet per second. But when there's no units given, don't give units. Very common mistake, see it all the time. Oh, it must be metric. Everybody loves metric. So you gotta be careful. Now, here's step 1 of calculus. What the heck's a secant line? All right, I'm going to draw this curve horribly on purpose. Okay, and I'm not drawing it correctly. I'm drawing it big and fat on purpose. Here's 3. Actually, 1 should be there. Here's 1. And what we just did was find the slope from here to here. Okay? And that is an average. And that slope is 12. That's what we just did. Really important you understand that. Really important you understand that. And again, I stretched it out so you could see that. Because now what we want to calculate is this right here. The tangent line at some point. Now, we're not saying where. Maybe it would have been this one. Maybe it would have been this one. We usually draw it out here as in somewhere between 1 and 3. But we wanted it at 2, then it would have been drawn here, so on and so on. So how do we do that? We use limits. Here we go. So let's think about this. All right, up here we had f of 3 minus f of 1 over 3 minus 1. We want 3 minus 1 to go to 0. We want this to go to 0. Now, if you're smart, you're going to say, we can't have that go to 0. We can't divide by 0. Well, that is the really slick thing that Isaac Newton did. And Leibniz, German counterpart. How do we find a slope of that tangent line where the gap has dropped to 0? Well, here we go. Let's just do it with y equals x squared. We want the limit as the gap, some gap h. So we're up here, it would say this gap h as it gets to 0. And we call this the x point. So x plus h is over here. And that is the definition of the derivative. And you're probably saying, but I can't take a limit as it goes to 0. I said, yes, we are. We just spent a whole unit doing that. So here's how we do it. And we call this the long way because there's a lot easier way to do this, as you will see in your very near future. Watch carefully. X squared minus x squared vanishes. H cancels here and here. We're left with two x plus h. Nothing on the bottom. Slick. H goes to 0. We're left with 2x. All right. And that's it. That's the answer. That gives us the slope. No. You didn't tell us what we wanted at. Okay, well, let's just say it's at halfway between 1 and 3. Let's say it's at 2. We would say at x equals 2. 2 times 2 equals 4. 4 feet per second, meters per second, whatever's being asked, but wasn't asked, so we'll just call it 4. Now, I just plucked that 2 out of thin air. Just as an example, we can plug in anything at x equals 6, and then it's 12. At x equals -4, that's negative 8, so on and so on. All right. That is the slope of the tangent line at 2. All my diagrams and my equations are changing back and forth. I want you to understand the concept. We'll do plenty of this going forward. There's a lot easier way. If you notice this is x squared, you throw the 2 out front, subtract 1, you get 2x. That's how you do it for a polynomial. Onwards. So I just did this. All right. And we'll do another example. All right. Slope of a curve at a point. Slope is a limit as we drop that x gap to 0, and we keep the top there. This is the quotient difference, something like that. It's the definition of the derivative. And they pick a point P at a comma f of a. All right, if we go back to our previous page, that would mean at this point and f of that point, whatever you get here, some a, f of a. And you need both those coordinates for most of the problems we'll do. We'll talk about that when we get there. Let's just do one, all right? 1 over x, find the slope, yada, yada. Okay, the slope is, find the slope at a. Limit as h approaches 0, f of a plus h minus f of a over h. Doing this really the long way. But hey, that's how we do math sometimes. 1 over a plus h minus 1 over a over h. This is something we're going to do a lot this year. So why you have to get good at fractions immediately, not sometime in your future. Common denominator. Equals limit as h approaches 0, a minus parentheses a plus h a plus h times a over h. Still haven't taken a limit. A minus a is 0, minus h is negative h over a plus h a over h. Cancel, cancel. Plug in 0, we get negative 1 over a squared. Now, at this point, you might say, well, I thought you just said you throw the thing out front. You put a 1 out front. I don't see how that works. Well, let's just look behind the curtain a little bit here. This is called the derivative. That's just basically everything we did. There's nothing confusing about it. People, oh, what did you just do? Derivative with respect to x. All right, rewrite 1 over x as x to the negative first. And what did I say? We throw the negative out front, and then we subtract 1. In other words, negative 1 over x squared, which is what you got. So that's the fast way, that's the long way. How often we have to do the long way? Not often, and you should always check it with the fast way. More on that when we get to Unit 3. All right, well, what else did it ask for? Find where the slope is negative 1/4. Negative 1/4 equals negative 1a squared. Negatives cancel. A squared equals 4. Square root. We put that in, so we need a plus or minus 2. Now here's the fun part. This actually makes sense. One over x graphs like this. And at plus or minus 2, the slope should be approximately negative 1/4. It's definitely negative. It's a negative 1/4. Well, it's impossible to tell from my quick sketch, but looks like we know what we're doing. All right, actually put in double tick marks, so 2, negative 2. So it actually works. It all ties together. You gotta know what you're doing. You gotta know this. So, as I said above, expression is called the difference quotient. Hey, look at that. I screwed it up here. That's really funny. Difference quotient, flip that around. All right. It's one of the 2 most important things we're gonna do this year. Can't overstate it. One of the 2 most important things we're gonna do this year. Get this down. Not all the nonsense we just did, the understanding that it's slope of a line, we can do it at a point, tangent line, not secant line, all that. Now, this is something when I was back in high school, we did a lot of. Suddenly it up and vanished. I think it's because we have so many other things we can do now that we have calculators and all sorts of cool math we can do. But normal line is just perpendicular. You do the whole flip-flop and negativize it. So let's do it the long way. Write an equation for the normal to the curve at x equals 1. You know what I need to do first is find out what that point is. It's 1 comma. So 4 minus 1 is 3. All right, I need that point. When I write an equation for a line, I need a point. So, all right, big ugly work to do. And then we'll do it the shortcut way to make sure we know what we're talking about. 4 minus x plus h squared. Is that the definition? Gee, I already forgot. Yeah, that's the definition. Minus 4 minus x squared over h. This looks complicated. Okay. Let's see what I got here. I got notes I can sheet and just copy, but let's see what I got. Minus x squared plus 2xh plus h squared minus 4, and I'm going to distribute this one, plus x squared. Oh, phooey. H. I'm a stickler for the proper notation because that just kills students when they don't do it right. Limit as h approaches 0. 4 minus x squared minus 2xh minus h squared minus 4 plus x squared all over h. and the magic of calculus. Stomp, 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 stomp. What do we call it? A cancel party? Trying to do justice to everybody's features. So we get negative 2x because when I plug in 0, vanish, negative 2x. Okay, let's do the shortcut way. This is a derivative, and it's 4 minus x squared. This is technically x to the 0, so when I put the 0 up front, it vanishes. The derivative of that is 0. And that equals negative 2x. Hey, look at that, negative 2x. How cool is that? All right, at x equals 1, so slope's negative 2. We want a normal line, m normal. Flip it and negativize it. Damn right, it's a verb. 1/2. And then the part that, holy moly, for some reason, people just don't want to do it. Y minus 3 equals 1/2 x minus 1. I throw the 3 over, y equals 1/2 x minus 1 plus 3. Don't simplify it, just leave it, because you're done. Why add more work if you don't need to? All right. By the way, you confused about this 4? Graph it and find the slope for me. Remember, this is a slope. Tangent line, slope, 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 slope. Yeah, that's right, slope of a horizontal line is 0. Fascinating. All right, so now we can find instantaneous change, not average rate of change. So t equals 1. Here's our equation. Limit. Let's do the fast way. Let's go backwards, or the way we'll do it going forward. What is the derivative? Notice it's a variable, so it's a t now. 16t squared. Well, we throw the 2 out front. 2 times 16 is 32t. And then we plug in 1, we get 32. And they didn't give us units again. It's very upsetting. I happen to know this one would be feet, but I can't make that assumption. Limit as h approaches 0. 16t plus h squared minus 16t all over h equals 16t squared plus 2th plus h squared minus, I don't know my squared here, 16t squared. Very upsetting. Limit as h approaches 0. Okay, I'll start getting rid of things. By. Plug in 0, see ya, equals 16 times 2t equals 32t. Hey, cool, we got it right. At t equals 1, instantaneous rate of change, I rock, equals 32. No units given, feet per second, meters per second. Nobody gave us units, so we don't put them in. You have now just taken a massive step forward into calculus, because all I'm doing now for the next, oh goodness, 3 months is going to be showing you how to take derivatives of things, apply those derivatives. That's it. So I really hope you caught what was going on there. Good luck and happy mathing.